We live in a world where the demand for high-dimensional data keeps rising. In applications ranging from modeling to simulation to animations and entertainment, large data such as high-resolution images and videos and 3D models are urgently being called for. A key challenge is how to compactly and efficiently represent such data digitally in a way that requires little memory yet still has strong representative power. One recent powerful idea is to use neural representations, where the data is encoded as parameters of a neural network. For example, for a 3D model, one can represent it with a neural network that takes in XYZ spatial coordinates and outputs occupancy or some other value of intended value. Now, by querying this network at multiple locations, one can recover the original object or the original surface. The problem with current neural representations is that they can take quite a long amount of time, many minutes or even hours, to be trained to represent data such as 3D models or gigapixel images. In this work, we present a method for encoding high-dimensional data as neural representations that is an order of magnitude faster than state-of-the-art methods. We accomplish this using a multiscale, patch-based method that leverages Laplacian pyramids, giving a multiscale implicit neural representation, or minor. We demonstrate this method on an image. Suppose we would like to represent this image as a neural representation. We first downsample it by a number of scales. We start with the coarsest scale. We divide it into small patches. Then, for each patch, we train a small neural network to represent that image. Repeating this for each of the patches, we have, in this example, 4 neural networks to represent each of the 4 patches, and finally we have a representation for the coarse image. This takes a short amount of time because the image is of low resolution. Now we move on to the next scale. We again break it down into small patches of the same size, and now we begin with our estimate that is an upscaled version of our previous estimate at the previous scale. Now, if suppose we want to learn the upper left patch of this image at this finer scale, we again initialize a neural network and train it to predict the residual from the patch from the previous estimate, and then we learn the finer patch. Repeating this for all the patches, we're able to now have an estimate or representation for this second scale image. Now we can move on to the finest scale. Now, when we upscale the image, one thing we can also do, and one thing we do, is to check which of the patches have already converged to be very close to the ground truth. For example, in this image, these 3 patches are already very close to the ground truth from the previous scales. And thus, when we break up the new image or the new scale into different patches, we no longer need to train on those respective patches. This cuts down on the required neural networks, cutting down on runtime and saving us on memory usage. Again, repeating the same procedure where each neural network learns the residual for each of the small patches, we are now finally able to represent the original image. This set of neural networks, each one learning a patch at a different scale, is our representation. This is minor. You will see in our paper that we test on various data, such as gigapixel images and 3D models, and we observe that minor is able to obtain high-quality results in a very short amount of time, a duration wherein state-of-the-art methods are still far from convergence. By cutting runtime by an order of magnitude, minor takes a major step towards convenient and efficient representations of high-dimensional data.